So the next one is Stephen Keith and Andrew Woods, two people which are quite well known here, two people who are often attending the SD&A conference. So Stephen Woods is, of course, sorry, Andrew Woods. I made a combination of both. Yeah. So he's leading this conference for a long time already. So he's from Curtin University, and I think you saw already his talk. It was on Monday, or?
I gave a standby talk on Monday. Yeah.
So Stephen was already participating in a lot of different projects. So he's free consultant at the moment. And so what we are looking forward now is a talk about bringing 3D map into the 21st century. So Andrew was already working on this, I think, a few years ago.
A long time, yes.
And now Stephen brought it into the future. So thanks a lot.
And I might point out that Stephen's been attending for many, many years, and this is his first paper, so he's got lots of experience and practice to give this presentation today. Thanks, everyone. 3D map is a paper from, 3D map was the tool I used to prepare a paper in 1993. This is it here, Image Distortions in Stereoscopic Video Systems. It was primarily part of my master's research, and it's been a very popular paper over the years. It's acquired over 500 citations since being published. And so the 3D map tool was developed to allow an analysis of the geometry of stereoscopic display from the capture system right through to the display system. So just imagine that there's a grid placed in front of the cameras, and then the software, the 3D map program, shows a grid here which illustrates how that grid would have been distorted, or how objects would, if they were sitting at those points, where they would appear in front of that display. There's a lot of detail that needs to be considered in terms of what different parameters. There's 3 parameters at the camera system: this camera separation, the field of view, which is determined by the focal length of the lens and the size of the imaging sensor, and also the convergence distance. At the display system, there's 3 parameters: the separation of the eyes, the viewing distance from the screen, and the size of the screen. And then there's 2 configurations that the cameras can be set up. They can either be a towed-in configuration where the cameras are angled inwards, or they can be set up parallel and then using sensor shift to achieve the convergence of the 2 views. So tow-in and the parallel configuration with the sensor shift. And then there's a series of equations which are used to convert firstly from object space in front of the cameras to the coordinates on the imaging sensor of the camera. And so there's an X and Y for both of the imaging sensors, which is defined by that equation. And then there's another equation to convert from the imaging sensor coordinates to screen coordinates. That's a pretty easy equation, just a magnification factor multiplication there. And then to the image space, there's another set of equations to convert from screen coordinates to the imaging space. So X, Y, and Z, which we'll be using here a coordinate system centered on the point between the 2 persons' eyes, and X, Y, and Z is calculated there. And if you join all of those equations here, you get this big mishmash here. Now, this was not something new. This was actually well known from the 1950s. The Spottiswoode brothers did this analysis. But one thing that was new in this work back in '93 was that their analysis back in the 1950s was based on the use of slide rules and manual calculations. They didn't have the advantage of using a computer to do all these calculations. And as a result, one thing that they missed, well, they couldn't perform these nice diagrams quite so easily, but the program allows this presentation here with the graph illustrating what distortions might be present. And here's the screen, here's the dismembered person's eyes. There's a line there which represents objects sitting at infinity, and this grid represents where objects would appear at different distances away from the camera. And so the 1950s analysis had simplified things to miss some of these distortions, and one of those was depth plane curvature, which we'll mention in a few slides. But the software allowed you to adjust the camera separation, decreasing or increasing, which would compress or expand the 3D space. It allowed you to increase or decrease the field of view, which would again compress or expand the 3D space. You could increase or decrease the convergence, which would shift the 3D space towards the viewer or away from the viewer. At the display system, you could also increase or decrease the eye separation. Don't try this in real life, it might be very painful. Which would increase or decrease again the depth range. Increasing or decreasing the screen width would have another unusual effect. Here you can see that it's starting to get closer to being orthoscopic, where the squares are a square. And you could also vary the viewing distance, and as you might expect, it compresses or expands the 3D space again. So the Spottiswoode brothers didn't notice this depth plane curvature, so if my memory serves me right, this was the first paper which sort of revealed that in an analytical sense, I should say. And so these depth planes are curved with the toed-in configuration. With the parallel with sensor shift, you don't get that depth plane curvature, so it was further reinforcement for using that particular configuration. The software could also simulate moving to the side of the display away from the point directly perpendicular to the display. The software also showed keystone distortion as well, which is the other reason that you try to avoid using the toed-in configuration. So with that, I'll pass now on to Stephen.
Steal the mic. Well, good morning, ladies and gentlemen. So you get a perspective on what's going on here. My profession has been a research support engineer. In other words, I'm the type of person that's supposed to support a person like him. So I'm not a researcher, I'm a software engineer. And when I first started thinking about this paper, when Andrew suggested it, like a drowning man who's seeing his life going before him, I saw my 42 years of all the workarounds and all the things that I have done to make this stuff work, and I'm sure you've experienced that as well. So the idea is we want to bring this code into the 21st century, and I present this slide is that I think even in the 24th and a half century, we're still going to have legacy code. My first job in 1974, I was given 25,000 lines of Hollerith code, of Hollerith cards, and I was told to fix it, maintain it. So wherever we're going to be dealing with code that has been developed anywhere from, a decade to a quarter of a century. So 3D map, first thing to know is that it's written in Borland C, used MS-DOS. Presently, it needs to have an emulator in order to run. It's not going to run on the Mac. It's not going to run under Linux or anything else. But there is a program available that you can use that can run that code. So here's some visual displays. As you can see, it's fairly typical of the kind of displays we had in the 1990s. And this is just about when computer graphics was beginning to blossom. Here's another example of what we saw. Now, the code is typical of legacy software. I will say that, fortunately, it was not written in Fortran or BASIC. And written in C. I'm very familiar with C. A lot of us are very familiar with that language. And comes the question, can we do a straight conversion? So to answer that question, let's consider these issues. I have three modules: how does scientists work, tools, and the marketplace. It turns out that these have a way of dictating our configuration. So how does scientists work? Now, this is my experience with something like 40 or so different researchers over the years. They select a subject to study. They think in terms of 30 years. What are we doing here now? We're about 25 years into your code right now, aren't we, Andrew? Okay?
Making me feel old.
Well, I'll make you feel better in a minute, okay? So what they do is they develop a software tool. So wouldn't it be really neat if I had a piece of software that could help me do my research? Well, it turns out in every instance, they're doing more computer science than science. So what they have to do is pretty much say, okay, I'm going to get the tool in a particular state, and then I have to abandon it because I have to do things like science. Okay? So that brings us to the concept of a tool. And so I brought up this slide. Probably you've heard this phrase, if the only tool you have is a hammer, you tend to see every problem as a nail. Now, in 1974, when I saw this, I went to Lockheed Research, and I saw this, and I said, what does this mean? Okay? Well, come to find out is that Maslow, what he meant was is that if you have a tool and you are successful with it, you're going to try to apply that to every other aspect of what you do. Okay? In other words, I have a colleague of mine, Dr. Jim Blinn, told me that if you can't do it in Fortran, you can't do it at all. Now, his concept of that has changed over the last 30 years, but that kind of gives you an idea. The other aspect is that the tool can also guide us, can push us through forward to what we want to do, but at the same token can limit us, okay? And I'll try to make that clear as we move on, okay? So here's the question. Well, here's the problem. What if that's the only tool you have? What if all you've got is a hammer, okay? And so we have all of these workarounds. And I'm sure as researchers and others, you've seen all of these workarounds. So we all work with what we can get. So what do we have at the time? I'm pretty much projecting what had been there because I wasn't there, okay? An IBM PC, Borland C or C++, and some limited graphics, early of which you saw. Now, here's the question is, where do we get those tools? We get them from the marketplace, okay? I'm doing a Monty Python thing, the marketplace, okay? Scientists depend upon products provided by that marketplace. But this is a hard lesson learned, and I discovered this in 1984. In 1984, the SGI Silicon Graphics machine came out. There was the IBM PC, and there was the Mac. And there was a war going on as to which was the best. Well, the SGI was certainly a better machine, and so one researcher, one presenter said, don't allow the marketplace to dictate to you what products you're going to use or tools that you're going to have. So I had this little revelation in 1984. The marketplace dictates what products you will use. The marketplace dictates what products will survive. Because you can't run around building computers or writing compilers and this sort of thing because you want to do science. So let's establish a timeline to get an idea of this marketplace. So 3 things happened in 1947. So that's I'm establishing as a timeline. The Association for Computing Machinery was instituted in June 1947. This guy was born in December 1947. And flying saucers landed in Roswell in 1947. So it kind of more imprint the idea of our timeline. So here is our timeline. I'm sorry, I'm using the wrong pointer here. Here's our timeline. And what we're going to be looking at are these 2 bar charts. Now, right here is the domain of the scientist. And they could have several of these, but it's typically 10 to 40 years they will do this. But the whole point is they know what they're doing. They know what they want to study. They know what they want to do. Okay? Right around here, computers are being built. We had things like Fortran, assembly language, tube-based machines, probably as big as or twice as big as this room. And this was a kind of typical market cycle. So what this is indicating is that, say, like, roughly every 15 years or so, I'm just kind of give a feeling that things are moving pretty slow. Then we started doing things like integrated circuits, transistors. We came out with the IBM PC. We had other languages like C and Pascal come about. And this is about when 3D map was created. Time marches on. We have 5-year cycles. We have a new Mac or a new PC or a new chip that's coming about. And not just C or C++, Algol, Pascal, Snowball, Lisp, Smalltalk, COBOL, a variety of Ada, PL1. I don't know if any of these particular languages are familiar to you, but I've used them all, okay? But it comes out for me, okay, this is the one thing, the C language and Unix are the one thing that have stood out over this entire timeline. Time marches on, our cycles begin to reduce. The marketplace is beginning to catch on in terms of developing products and tools. 3 years, 3 years. Now we're getting close to the present. We have Android and iOS, a whole different way of programming these devices. Okay, 2 years. And I dare say we're now getting to 1 year. I mean, they're already talking about, what, iPhone 8 or something, and different programs. So here's what happens. How do I bring this item into the 21st century? And here's the other aspect I want to bring about Maslow's statement about hammers. About this time, I want you to think of hammers are not just tools. They're concepts, they're ideas, they're methods, okay? Now, the scientists has pretty much always had the scientific method. The tools for developing software and applying engineering aspects to this was a very slow growth, and so they have their own methods of determining development. But at that time, what kind of coding practices did we have? What kind of machines did we have? All of these things are embedded in this code. And here's the weird thing about code. You know, if I were to ask you the question, what is code? And if you program, you immediately think, oh, it's the lines that instruct the computer what to do. Then I ask my students, where does that code come from? Click, 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 click. Oh, it came out of my brain, okay? You are taking concepts and thoughts, and you're encoding them, you're crystallizing them in code with all the techniques that you have in here. So it's just more than lines of code. It's concepts, it's scientific theory, it's the methods of that time, and how do I bring them up to this point, okay? So now we can ask the question, with that particular background, can we do a straight conversion, okay? How do we convert code using techniques from 25 years ago? I don't mean to imply that it was improper or anything like that. It's just what we did then, okay? And I did these things. I looked at the code and immediately recognized the techniques and practices that we applied at that time, okay? How do we bring it into a modern environment, keeping in mind we have things like iOS and Android and foundation libraries and so forth? So the first thing I do, so I'm kind of segueing in here to getting to a conclusion here. So what do we need? Well, I want reusable code. I want that code to be usable on other systems. Right now, we have to use an emulator to use what we have. I want it to be multi-platform. Specifically, I want to be able to use the predominant devices that we can use that we're accessible to is under the Mac and Windows. And something that's extremely important is you want one source for all platforms, because I've worked in a variety of research areas. If you take a piece of code and you give it to another researcher, another person, it mutates. It develops new limbs and other things. And so and just taking it to a different platform, you're going to, within a year, you'll see totally different code. Or you recognize code that's there, but it will totally mutate, okay? So the other thing we need is establish a criterion for what we've got. Well, fortunately, we have the paper for us. And the other thing, what do we want the 3D map code to address? Well, fortunately, it's already in C. It does use a technique where the code is just in one program, one module. As a software engineer, I like to break up the individual elements, so once it's tested, once it works, you don't mess with it. And you reduce the coupling of any problems in the code. All the graphics drawings are fixed. Now, he has a method where you can expand and move things around, but I wanted to bring it up to develop them to a modern set of techniques using modular developments. So here's the crux of it. Here's the conflict. I'm going to use a modern tool to update the code, but I'm going to do it without violating his ability to access what that code does, should he have to change it. Should I go away somewhere, okay? Well, I could use C, OpenGL, and GLUT. This is my typical environment. Unfortunately, GLUT has been deprecated. There is free GLUT, but in order to produce a cross-platform set of code, it takes a whole lot more time. There's this processing thing called processing.org. It's a very C-like language. It's in Java. It's a language similar to C. You can create cross-platform executables. It requires Java as a foundation. And easy, fast prototyping, and it's free. And this is something what it looks like. And then there's this other environment called Socio, which I could use. It's very professional, but it's costly. So this gives you a little idea of what is going on there. So I decided to use processing. I didn't have a lot of time. Useful for rapid prototyping, C-like. So let's see what we can do. Recall this image. And now we can do this. Okay, so here's converged, here's parallel. If you want to print it, we can put it out in black and white and black. I can also include the variables that we have there. It also uses certain techniques for graphics, so I made them modular, so we can create little modules so we can rotate and translate the items. So I can do things like this. Okay. Other additional items I've included is a bar that says how do you control the keys, display of the variables, and but before I can move further with that, and I got 28 seconds, okay, is I need to convert. I want to see where I'm going to go. Now, some of the code is still broken. I have to talk to the researcher about how we deal with that and where we want to go with that. And there we go. By the way, this is the URL for the paper. So let's see. Well, yeah, okay. I'm going over time here. Sorry.
Yeah, thanks a lot.